Franz Reichelt believed a piece of clothing could turn a falling pilot into a human parachute. In 1912, airplanes were still fragile machines made from wood, fabric, and wire. Pilots had no reliable way to survive if an engine failed or a wing collapsed. Reichelt, an Austrian-born tailor living in Paris, believed the answer was simple: a suit. When the wearer spread his arms, the fabric would supposedly unfold into a wide parachute. The pilot would fall, the suit would catch the air, and the ground would become survivable. It was elegant, it was compact, it was also dangerously unproven. Reichelt tested early versions with weighted dummies dropped from the 5th floor of his apartment building. Some appeared to descend gently. Others struck the ground with enough force to destroy the frame. Each failure produced another adjustment: more fabric, different folds, new straps, a heavier canopy. The failed tests should have answered the question. Reichelt decided they had only been launched from the wrong height. He petitioned Paris authorities for permission to test his parachute from the Eiffel Tower. The request was eventually approved, but officials believed a dummy would be used. Reichelt arrived on the morning of February 4, 1912, wearing the final version himself. Journalists gathered. Cameras were ready. His friends tried to stop him. Reichelt climbed to the first platform, more than 57 meters above the ground. He stood on a stool placed beside the railing. The parachute suit hung around his body like a folded cloak. He checked the wind. He adjusted the straps. Then he stepped onto the edge. For almost 40 seconds, he hesitated. Then he jumped. The suit did not open into a parachute. The fabric folded around his body, and he dropped almost straight down. He struck the frozen ground beneath the tower and died instantly. The invention designed to save falling pilots had performed exactly one full-scale human test. Its inventor was the test subject. The Eiffel Tower had become a laboratory, a stage, and a grave. Otto Lilienthal spent years studying flight before powered airplanes existed. Born in Prussia in 1848, Lilienthal became one of the first people to treat human flight as an engineering problem instead of a fantasy. He measured air currents. He studied bird wings. He built gliders with wooden frames and stretched fabric. Then he flew them. Between 1891 and 1896, Lilienthal completed thousands of gliding attempts from hills near Berlin. He often launched himself into the wind, balancing beneath the wing like a man hanging from a giant kite. His flights were short, but they were controlled. He proved that a person could leave the ground and return without immediately becoming a falling object. His work influenced the Wright brothers and many other early aviation pioneers. But Lilienthal's gliders had a serious weakness. The pilot controlled the craft mostly by shifting body weight. If the wind changed suddenly, the entire glider could roll or pitch before the pilot had time to react. On August 9, 1896, Lilienthal launched one of his newer gliders from the Golenberg Hill. The flight began normally. Then the glider lost lift. Lilienthal tried to correct it, but the craft stalled at an angle. He fell from roughly 15 meters, landing hard on his head and spine. He was carried back to Berlin with a fractured vertebra. For several hours, he remained conscious. His brother Gustav was at his side. The next day, Otto Lilienthal died. His gliders had made him famous because they turned falling into controlled movement. In the end, one uncontrolled fall ended the life of the man who had made flight practical. He had spent 5 years learning how to leave the ground. The ground still had the final argument. Horace Hunley designed a machine that could attack warships from beneath the water. During the American Civil War, the Confederate side had fewer ships and fewer resources than the Union Navy. Hunley believed an underwater vessel could bypass the enemy fleet completely. The submarine was called the H.L. Hunley. It was a narrow iron cylinder powered by hand. 8 men sat along a central crankshaft and turned it together. A 9th man operated the controls. There was no electric motor, no modern air system, and no comfortable escape route. The crew moved through darkness inside a metal tube filled with machinery, condensation, and stale air. The Hunley sank during training exercises in 1863. Hunley and several crew members died. The submarine was recovered, repaired, and returned to service. It sank again. The boat was raised once more. It was repaired again. The deaths were treated as evidence that the design needed improvement, not that the mission should end. On October 15, 1863, Hunley personally joined another test inside his submarine. The vessel submerged in Charleston Harbor and failed to return. Searchers found the wreck on the bottom with Hunley and the entire crew dead inside. The submarine was lifted, inspected, and put back into operation anyway. In February 1864, the Hunley attacked the Union warship USS Housatonic. It became the first submarine in history to sink an enemy warship during combat. The victory was extraordinary. So was the price. The submarine vanished after the attack. Every man aboard died, including the inventor whose name it carried. Hunley created a weapon that could defeat a warship. It could not reliably bring its own crew home. John Godfrey Parry-Thomas believed speed was an engineering problem that could be solved with enough power and courage. Parry-Thomas was born in Wales in 1884. He became an engineer, a designer, and one of Britain's most determined racing drivers. He worked with the Leyland Motor Company and developed machinery, engines, electrical systems, and automobiles. But his greatest obsession was the land speed record. He purchased a massive vehicle called the Hyam Special and rebuilt it almost completely. The car carried a powerful 12-cylinder aircraft engine. It was loud, enormous, and difficult to control. Parry-Thomas renamed it Babs. In April 1926, he drove Babs across Pendine Sands in Wales and set a world land speed record of more than 170 miles per hour. The beach became his proving ground. The car became his mechanical extension. But Babs was not a modern racing car. Its drive system used exposed chains to transfer power to the rear wheels. Those chains were later covered by aerodynamic fairings, but the machine remained violent and unpredictable at full speed. In early 1927, Malcolm Campbell broke Parry-Thomas's record. Parry-Thomas returned to Pendine Sands to take it back. On March 3, he entered the measured mile at high speed. The car began to slide. It lifted, rolled, and struck the sand. Early reports claimed that one of the drive chains had broken and hit Parry-Thomas in the head. Later examinations suggested that the fatal injuries were more likely caused by the crash itself. As Babs rolled and slid across the beach at more than 100 miles per hour, Parry-Thomas died inside the machine he had designed, rebuilt, and trusted. After the inquest, Babs was buried in the dunes. For 42 years, the car remained underground. Then an engineer named Owen Wynne Owen recovered it and restored it. The machine eventually returned to display. Its driver did not. Valerian Abakovsky tried to make trains fly without leaving the ground. In the early Soviet Union, engineers searched for faster ways to cross enormous distances. Railroads were slow, expensive, and vulnerable to poor infrastructure. Abakovsky believed a railway car fitted with an aircraft engine could solve the problem. His invention was called the Aerowagon. It looked like a small rail vehicle with a propeller mounted at the front. The idea was simple. The wheels would guide the vehicle along the track, while the aircraft engine pushed it forward at much higher speeds. The Aerowagon was tested in 1921. It could travel faster than ordinary trains, but high speed on imperfect railway tracks created a dangerous problem. A plane could rise above a rough surface. A rail vehicle could not. Every defect in the track remained connected directly to the body of the machine. On July 24, 1921, Abakovsky carried a group of officials from Moscow toward the city of Tula. The trip began successfully. The Aerowagon reached high speed and appeared to validate its design. During the return journey, the vehicle derailed. It left the tracks at speed, broke apart, and killed Abakovsky and several passengers. The machine had combined the worst features of two technologies. It had the speed of an aircraft, but the limitations of a train. Abakovsky wanted to shorten the distance between cities. His invention shortened the distance between speed and catastrophe. Thomas Midgley Jr. created inventions that changed modern industry and later became symbols of technological danger. Midgley was an American chemist and engineer. In the 1920s, he helped develop tetraethyl lead as an additive for gasoline. The chemical reduced engine knocking and allowed automobile engines to operate more smoothly. The product was commercially successful. It was also toxic. Workers involved in its production suffered hallucinations, tremors, paralysis, and death. Midgley himself demonstrated the chemical by pouring it over his hands and inhaling its vapor during a public presentation, insisting that it could be handled safely. He survived that demonstration. Years later, Midgley worked with chlorofluorocarbons, or CFCs, which were used in refrigeration and aerosol products. At the time, they were praised as safer alternatives to earlier chemicals. Decades later, scientists discovered that CFCs damaged the ozone layer. Midgley did not die directly from leaded gasoline or CFC exposure. His final invention was more personal. In 1940, he contracted polio and lost much of his mobility. He designed a system of ropes and pulleys to help lift his body from bed. The device allowed him to move with less assistance. It was a practical machine made for one specific user. On November 2, 1944, Midgley became entangled in the ropes of his own lifting mechanism. The system tightened around him and strangled him. He had created a device to escape the limitations of his body. The mechanism used those limitations against him. Henry Smolinski believed the family car could become an airplane. In the late 1960s and early 1970s, flying cars were still presented as a near-future possibility. Smolinski, an engineer trained at the Northrop Institute of Technology, decided to build one himself. His concept was called the AVE Mizar. Instead of designing a completely new aircraft, Smolinski combined two existing machines. The front section came from a Ford Pinto automobile. The rear section came from a small Cessna Skymaster aircraft. On the road, the car could supposedly function as an ordinary vehicle. At an airport, the car would attach to the aircraft section and become a small plane. The idea looked efficient. The problem was the connection between the two halves. Cars and aircraft are built around completely different stress patterns. A car absorbs bumps through its suspension. An aircraft must remain light while surviving vibration, torque, and aerodynamic force. The Mizar required both systems to coexist through attachments that had to carry enormous loads. Smolinski conducted early flight tests in 1973. The aircraft portion flew, but the project remained unstable and experimental. On September 11, 1973, Smolinski and test pilot Harold Blake took one of the prototypes into the air near Ventura County, California. Witnesses saw the wing strut fail shortly after takeoff. The aircraft section separated from the car body. The Mizar lost control and crashed, killing both men. Smolinski had tried to make transportation more convenient by combining two machines. The connection failed because neither machine was willing to become the other. Karel Soucek built a barrel meant to survive the most famous waterfall on Earth. In 1984, the Czech-Canadian stuntman designed a reinforced barrel with shock-absorbing material and a camera system. His goal was to ride inside it over Niagara Falls. The stunt was dangerous, but the barrel was designed specifically for the impact. It had a rounded shape, a protective interior, and enough buoyancy to keep it from sinking immediately. On July 3, 1984, Soucek entered the barrel and was pushed into the Niagara River. The barrel went over the falls and survived. Soucek survived too. He emerged bruised but alive, and the successful stunt made him famous. He began planning a new attraction built around the barrel. He wanted to recreate the drop indoors, from the roof of the Houston Astrodome, before an audience. The new stunt was not a waterfall. It was a controlled vertical drop into a tank. That change created a different problem. The barrel needed to strike the water at exactly the correct angle. If it hit the tank wall or entered crooked, the impact would be concentrated in one place. On January 19, 1985, Soucek climbed into the barrel at the Astrodome. The device was released from the roof. It struck the edge of the water tank instead of entering cleanly. Soucek suffered massive injuries and died shortly afterward. The barrel had protected him from Niagara Falls. It could not protect him from a poorly aligned landing. These deaths are often described as accidents, but accidents are rarely just one moment. They are usually a chain, a warning ignored, a material pushed past its limit, a test repeated after failure, a machine treated as a partner instead of a threat. Franz Reichelt saw failed parachute tests and blamed the height. Otto Lilienthal understood the air better than almost anyone alive, but his glider still lacked a reliable control system. Horace Hunley created a submarine powerful enough to destroy an enemy ship, while its own crew remained trapped inside a machine with almost no margin for error. Parry-Thomas turned an aircraft engine into a land vehicle and then asked it to survive at more than 170 miles per hour. Abakovsky placed aircraft speed on railway tracks. Midgley built a rescue system that became a strangling device. Smolinski joined a car to an airplane and discovered that two incomplete machines do not become one complete machine simply because they are bolted together. Soucek survived the world's most famous waterfall, then died in a tank built to imitate it. The irony is not that these inventors were foolish. Most were not. They were capable, ambitious, technically gifted people who saw a problem and constructed an answer. Their fatal mistake was not always ignorance. Sometimes it was confidence. The inventor knows every weakness in a machine. That knowledge can create caution. It can also create familiarity. And familiarity makes dangerous things feel ordinary. A parachute becomes clothing. A racing car becomes an extension of the body. A submarine becomes a workplace, a pulley becomes furniture, a barrel becomes a vehicle. Then the machine fails, not as an abstract system, as the object directly beneath, around, or attached to its creator. The final lesson is not that invention is reckless. It is that every invention eventually becomes a physical argument between human intention and the laws of nature. Nature does not care who designed the machine. It only cares whether the design survives contact with reality. And sometimes the first person to discover the answer is the person who built it. They solved the problem. The solution was fatal.